going to start Chapter 5, which is about alkenes. Chapter 6 it has a lot more detail about alkenes, specifically the reactions of alkenes. But in this chapter, we're going to learn a little bit about alkenes, naming a few properties, and that sort of thing. First, before you watch this video, I suggest that you read page 183 and the top of page 184. Pretty short read. So, what are alkenes? Well, alkenes are compounds that have a carbon-carbon double bond. Obviously, you already knew that. But, just to be clear, not arenes. In other words, not aromatic compounds. Aromatic compounds also have carbon-carbon double bonds, but there's a special situation where you have a 6-membered ring and 3 double bonds alternating, double, single, double, single, double around the ring. That's a special situation. Those double bonds do not behave like alkenes. So, let's talk about bonding. First of all, model number 1. Lewis dot structure, and of course VSEPR is included in model number 1. You might want to read section 5.1a before you go on with the video. Here are several different ways of representing a carbon-carbon double bond. Each one has, besides the double bond, has 2 other groups on this carbon and 2 other groups on this carbon. That's what these lines represent. Sometimes you'll see them drawn this way, sometimes you'll see them drawn this way. What should the bond angle be? Well, if it's got 3 groups, therefore trigonal planar and 120-degree bond angle. So this is a more realistic way of drawing it. These suggest 90-degree angles, which is not correct. But again, most of the time, Lewis dot structures don't really show the shape. Okay. So as I said, trigonal planar, 120 degrees. If you actually measure the bond angle, in most alkenes, it turns out to be 120 degrees or very close. So here's the question. Even though we know that each carbon has 120, 120, 120. Are they flat? In other words, is it the same plane as suggested in this picture, or drawing it in this way in this picture, or in this way in this picture? Or is it skewed off so that one of them is in a plane vertical and the other one is in a plane horizontal, drawn this way perhaps, or drawn this way? In other words, this structure, is it this way or is it this way? Notice in this molecule, this being a 3D model of the ethylene molecule, that both carbons are flat, and notice that the plane of carbon number 1 and carbon number 2 are in the same plane. Well, the VSEPR model can't help with that, because the VSEPR model can only tell us the shape around a particular atom, not the shape of the whole molecule. So, what do we do as scientists? Well, if a theory doesn't explain facts, we need to refine the theory or get a new one. So we move on to model number 2. Now, just to be clear, philosophically, does that mean that model number 1 needs to be thrown out? No, model number 1 still works in most cases, and so we use it. We just have to be aware that it has limitations and that it really is based upon model number 2. So, how do we use model number 2? Well, we have to draw atomic orbitals. How do you do that? Well, first of all, you decide the hybridization of all the atoms. Both carbons are sp2. Then you draw an sp2 hybridized atom. This happens to be carbon. Remember what an sp2 hybridized carbon looks like. It has sp2, 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 3 atomic orbitals pointing towards the corners of a triangle. In other words, trigonal planar. And then it has a p orbital sticking up and down perpendicular to the plane of the other 3 orbitals. I've drawn it twice because we're going to have 2 different sp2 hybridized atoms. Then you turn one of them so that these 2 orbitals point towards each other, and you draw them so they overlap. So notice that this is an sp2 hybridized carbon with its sp2 orbital overlapping with the sp2 orbital of another sp2 hybridized carbon atom. And notice that the p orbitals are parallel to each other. Then you do that for all the other atoms that are involved. In this case, since we're just doing hydrogens, that's easy. An s orbital there, an s orbital there, an s orbital there, and an s orbital there. So all alkenes have 2 sp2 hybridized carbon atoms bonded to each other, and the 2 carbons and the other 4 atoms are all in the same plane. And the reason for that, of course, is that so these p orbitals can overlap. They can overlap best if they are parallel with each other. If they're skewed off a little bit, then they can't overlap as well. And that means the other 4 atoms attached in these positions have to be in the same plane as each other. And what that means is rotation around that double bond is restricted. So notice this is an alkene with 2 groups. I'm calling them A and B on this end of the double bond, and 2 groups, again, I'm calling them A and B on this end of the double bond. Could you rotate it so that this A rotates down here and the B rotates up there, so that instead of being next to each other or on the same side, the A's are across from each other. Theoretically you could, but in fact that does not happen. Again, our model explains why that does not happen, because this is way more stable if the p orbitals are parallel to each other. In order to rotate, they would have to get out of being parallel with each other and then rotate back into parallel, so that the A on this end of the molecule would rotate up and then over to this position where the B is, and the B would rotate back to where the A is. But again, to make that happen, the p orbitals would have to become not parallel, so they couldn't overlap as well, and so that would take a great deal of energy, and that just does not happen. So again, this stuff here is the theory, this is the fact. Rotation around